Yeah, well, thank you so much for the invitation. It's a real pleasure to have the opportunity to speak to you about this topic, and a great opportunity to put together a talk on something I've wanted to talk about for a while now. So this is a new talk, but hopefully trying to bring together a few bits of work we've been doing in this context of the search for life. And I wanted to start with one aspect of the search for life, which is sort of illustrated by this kind of video in the background here, which is the Green Bank telescope, 100-meter, searching for signs of extraterrestrial intelligences. So sort of searching for the active broadcasts of life in the galaxy reaching Earth. And I want to use this to kind of build a statistical framework, which I'll keep coming back to for most of the talk, which I think it really kind of helps frame our understanding of what we're doing in searching for life and what the challenges are inherent to that quest. So imagine we've got a population of planets. Here are some planets. These are all the planets we know about or know how to observe. Some fraction of these maybe have aliens on them. Maybe they host life. And this is about as accurate or informed a picture of alien life that I'm going to give you in this talk, so apologies now. It's not going to get much better than this. But some fraction of these planets have aliens on them. And the question is, how do we find that fraction of planets that does host life? Obviously, the alien is not what we observe. What we observe is some evidence for life on a planet. So that might be, generally speaking, a biosignature, a sign of life on the planet. Now, there'll be planets which host biosignatures without hosting any life. And there'll be some planets where there's both life and the biosignature, and there'll be planets which maybe have life but aren't producing that biosignature. And we can think of this kind of in a statistical sense as we've got true negatives. This is the set of planets which neither have life and also are not evident, not producing any fingerprints in their atmospheres or otherwise of hosting life. So we're not going to be misled by looking at these planets. The false positives are over here. This is a set of planets that are producing some fingerprint of some sort of hosting life, but in fact don't have life, don't have aliens on them. This group of planets, they are hosting life, but the life hasn't imprinted itself on the planet in a way that we're able to observe, at least given this particular biosignature, whatever we've chosen to look for to fingerprint the presence of life. It's only this middle population where we have the true positives, where we both have the life and the evidence for it that we're able to detect. Now, this is interesting in the context of the search for extraterrestrial intelligence, or maybe technological instantiations of life. Because what this is doing in this kind of framework is actually moving the biosignature circle kind of pretty much on top of the alien circle. What it's really doing is reducing the number of false positives. And the kind of premise here is the nature of the signal is so inherently biological or the result of technological life that it's sort of impossible to mistake it for something that just arose naturally in the universe from abiotic processes. So this kind of statistical view is really sort of at the heart, in a sense, of the power of the search for technological instantiations of life. It reduces our false positive rate potentially to almost zero. It does have a potential problem, though, or a challenge in searching for life in this way. And this is the way maybe this kind of search for life is perhaps the one that sits most prominently in the public consciousness of what we're doing in looking for life, because of the long history for searching for broadcasts from other worlds. And obviously, the potential problem is evidenced by a reflection of the history of life on Earth. So this is a timeline looking back over 2.5 billion years. This kind of zoom in at the far right is about 2.5 million years in which, that's the period of time in which modern humans arose. And this is obviously a tiny fraction of the last 2.5 billion years, and an even smaller fraction of the 4.5 billion years of Earth history. And if we look back at the history of life over this period, then the kind of t equals naught is, probably the hard reset or the hard start for Earth was a bit after its formation 4.5 billion years ago, when the moon-forming impact occurred, extensively remelting the planet, probably ejecting much of its atmosphere, but giving us a very massive satellite that's probably been pretty important for Earth's subsequent evolution. So life must have arisen after this point, and you can push back in the geological record and get to about 3.5 billion years ago, finding evidence of life. But that's a sort of fossil record. Life's first major impact on the chemistry of the planet was about 2.5 billion years ago, when cyanobacteria, in producing oxygen, dioxygen, overwhelmed the capacity of the planet to consume oxygen by rusting rocks, by basically producing rust, and filled the atmosphere with oxygen. And the biosphere we occupy today is the ancestor of this chemical transformation of Earth 2.5 billion years ago. But actually, even though oxygen levels became high in the Archean back here, it was then about 2 billion years later before we even got the earliest evidence of animal life. So this is Charnia, a fossil you can find in the UK, about 570 million years old. So just before the Cambrian explosion here, which gave us the animal life that we're descendants of. So life on Earth as a technological instantiation is incredibly young. And I really like this graphic, which kind of shows a sort of impression of the Milky Way, us in our kind of suburban location out here in it, and the tiny bubble of space that's been influenced by our kind of technological broadcasts, our radio emissions over the last 2 centuries. So the footprint we've had in the galaxy as a technological species is extraordinarily small. So what this means for the search for intelligent life or technological instantiations in the kind of language of David Kipping is that whilst it may be true that we've minimized the false positive rate by looking for this, gratuitously non-abiotic signal, like a television broadcast, the actual population of planets that give rise to technological instantiations may be vanishingly small. We don't know, but it could be extraordinarily small. So what I suggest is we should mostly be looking for biosignatures in a kind of more general sense. So in a sense, a technological broadcast is a biosignature, but it's a very particular one. What we really want to be doing is looking for biosignatures much more generally, just the impression that life has left on a planet, whether it be the rock record of the planet as we search the surface of ancient Mars for evidence of past life, or in the context of exoplanets, obviously an impression this life has left on its atmosphere and its atmospheric chemistry. And that probably is the meaning of biosignatures we're most familiar with now in the context of exoplanetary science. But really, this is a search that's undertaken on Earth, looking back into the geological record, on Venus, on Mars, and in exoplanets, all in different ways and with different tools, but all of them essentially looking for biosignatures, perturbations to the natural system that can only be understood as being a consequence of life. But the problem with biosignatures, the potential challenge with biosignatures in this general sense compared to technosignatures, is there's this false positive rate. We can sort of articulate this kind of Venn diagram representation of the statistical framework in a Bayesian sense. And actually, there's a recent paper on arXiv by Rudy Arthur, Nathan Main and co. that really kind of communicates this quite nicely. What's the probability of aliens given a biosignature? Given some observation, which we think is potential evidence for life, what's the actual probability that aliens produce that? We can write this in the standard way. We've got the likelihood and then a prior, the probability of aliens. This is the probability of the biosignature given aliens. Linking this to our Venn diagram up here, this denominator term is just the probability of the biosignature, and the whole thing can really be understood as a ratio between I think I'm killing these one by one. A final. Is that going to work? Nope. Keep going. A true positive rate to a true positive plus false positive rate. And the false positive rate is all these planets exhibiting the biosignature that don't actually host life. So we want to maximize this probability of aliens given the biosignature, and what that means is, minimizing, practically speaking, minimizing the false positive. We want to make this term as small as possible so we can have the most confidence possible in our search for life that what we've observed, which is just going to be a signal of some sort, an impression in a rock, if it's early Mars, or a molecule in the atmosphere of an exoplanet, is indeed from life and not from any other process. So how do we do that? How do we avoid false positives? And what I'm going to suggest, in a sense, what most of our work focuses on, is that critical to this quest for finding life is actually understanding the context. And really at its heart is a search for understanding the planetary context in which we're observing the signal we're seeing. We need to know what we're looking at. And then given that, we can understand whether the signal we're seeing is potentially biological in origin or not. And I'm going to kind of develop this idea over the remainder of the talk and keep coming back to this kind of graphical representation of the statistical framework, because I think it illuminates some really interesting properties of the problem that goes beyond merely the kind of astrophysical part of this to, touching on the biology and the prebiotic chemistry as well, and the origin of life question itself. So to illustrate this, first of all, the importance of context, I want to come to this molecule. This is phosphine, a molecule which has gained a degree of attention and perhaps notoriety over the last few years in the search for life in the solar system. It's a molecule that Clara Souza Silva pointed out in 2020 is almost uniquely on Earth produced by life. There are very few, or almost no, non-biological sources of phosphine on Earth. So in that sense, it's a molecule which seems like an ideal biosignature. There's almost no mechanism on Earth to reproduce it in appreciable quantities. Where it is produced is in wetlands or swamps, regions where there's low oxygen and there's a lot of decaying organic matter. So this is a beautiful aerial image of the wetlands of Tierra del Fuego. You can see all of these flooded areas where organic matter is decaying. These are going to be sources of phosphine. However, we know from the solar system that phosphine is abundant in the atmosphere of Venus, of Jupiter as well. So here we're seeing the same molecule in a completely different context, now not on an Earth-like planet, but in the atmosphere of Jupiter. So just with this kind of framing here of a biosignature in the context of all planets, we see there's a significant potential for false positives here. We've seen the same molecule in two settings. Is it life in both cases that's producing phosphine, or is it abiotic processes? Well, of course, for Jupiter, if we add context on, we know that the likelihood of life producing phosphine in Jupiter is vanishingly small. It's an environment which, given everything we know about life, seems enormously hostile to the presence of life in Jupiter's cold, deep atmosphere, dry, cold atmosphere. So here we can understand the phosphine as simply being, yes, it's a biosignature, but given the context, it doesn't evidence life. It's simply an abiotic product of a hydrogen-rich atmosphere. Now, what we really want in our search for life is we want to look at those planets where the context is favorable for life to exist. So we don't want to have our context kind of bubble down here where it's primarily overlying lifeless planets and planets that can mimic the biosignature. We want our context to overlap with the occurrence of life, of aliens, and preferably overlap as little as possible with the biosignature planets, so that there's minimal possibility for false positives, so that most of the time when we see on these particular planets where the context is right, which could mean, say, the geology, but it could also mean the astrophysics. It could mean the right type of star, the right location of the galaxy, the right time in the age of the universe. When the context is right, we see that biosignature and we think more likely than not it's the result of life rather than a false positive. I just want to pick this diagram apart because I think it's really interesting, and it touches on some interesting aspects of this search for life. This region of the diagram over here, these are the lifeless planets, but they're lifeless habitable planets. So this is telling us something about the rate, so if our context was an Earth-like planet around a G-type star, so a temperate world, this would be telling us something about the rate at which these planets don't, abiogenesis doesn't occur on such planets. And this is something we could actually get an insight into through the exploration of Mars, a planet which also in its early history was transiently wet and warm. It was a rocky planet in many respects like Earth. Did life emerge on Mars and then was kind of quenched by its climate breakdown? Well, that's something we can potentially answer with sample return and robotic exploration of Mars. And we might even in the solar system or from solar system observations get an idea about the difficulty essentially of abiogenesis. How much of this green circle lies outside of the alien circle. This region here in white is the life as we know it. It just doesn't happen to be producing a biosignature. So it's kind of it's not detectable from our perspective using this particular biosignature to look for life. This region down here, the red region, is life as we don't know it. It's life that shouldn't exist given the context. So this is life on planets that we would deem perhaps uninhabitable, yet there's life there. So this is kind of capturing some of our ignorance about what life is, what it can tolerate, what it needs in the first place to emerge on a planet. This yellow region is the discoverable life. It's on a planet we think should be habitable, and it's producing the biosignature. It's producing the imprint on the atmosphere that we expect life to be making. This is our false positive rate up here. It's those planets which are habitable, don't have life, and are somehow contriving to produce the biosignature anyway. And of course, we want to minimize this as much as possible. So looking at some of these terms together, the life as we know it that's not producing a biosignature, and the life as we don't know it that we think shouldn't even be there at all, this is our false negative rate. This is the life that we're just not going to see with using this particular biosignature. These lifeless habitable planets and the fraction of them that are producing life, this is our abiogenesis rate. So this is a rate ultimately rooted in prebiotic chemistry and the early planetary environments that support prebiotic chemistry and the emergence of biochemistry. Now we can build context into our Bayesian framework here. This is something that David Catling has looked at, and Teresa, working in the IRA, has kind of built upon recently, and I'll come back to Teresa's work later in the talk. So we're looking for aliens given the biosignature, but also context. We need to put context central to our quest here. And in this framework, what comes out as very important is the likelihood, the probability of the data given the hypothesis, the probability of the biosignature given the context and given aliens, given the presence of life. So we'll look at this term next, and then we'll also come back and look at this second term, the prior, the probability of aliens given the context as well. We'll try and pick apart these two terms in the talk. So the solar system is a fantastic example of some of the challenges and opportunities for looking for life. And I'm going to emphasize this using Earth and Venus in the first instance, and the particular biosignature of ozone. So life on Earth, as we said, has flooded the atmosphere with oxygen from about 2.5 billion years ago. And it did that by overwhelming essentially the chemistry of the interior of the planet, which left to its own devices would strip that oxygen back out of the atmosphere to vanishingly low levels. So the presence of oxygen, or its photochemical product, ozone, is a striking sign of life on Earth and its impact on the surface environment. So ozone is a great example on Earth, given the context of an Earth-like planet, of or would seem to be, great evidence for life and a biosignature that would kind of safely land us in this true positive zone. Life as we know it, discoverable life. However, even Earth has a cautionary tale for us here, and that is, of course, that for about half of Earth history, ozone simply wasn't in the atmosphere. Life, for whatever reason, probably through some combination of biological innovation needing to take place, so oxygenic photosynthesis was evolved, but also probably also just simply through the mass of life, the abundance of life on Earth, had yet to overwhelm the reducing volcanic gases being emitted, such that the early atmosphere of Earth was dominated not by ozone, but by molecules like methane. And here we've got our classic kind of artist's impression of the early Earth, volcanoes spewing these reduced gases to the atmosphere, which early life had yet to overwhelm. So we even with ozone, what seems like the kind of the classic atmospheric kind of biosignature fingerprint, we know very well that Earth, for half its history, would have returned a false negative, using ozone as our kind of search criteria. What about false positives? Well, there's also a potential issue for false positives with ozone, looking at the solar system planets. And what's important here is to recognize how similar Earth and Venus are. Certainly looking back at the solar system as an exoplanetary system, we're looking at two planets that are overwhelmingly similar. They're within 20% of the mass of each other. They've effectively got the same radius. They orbit very similar distances from the sun. So the question you'd have looking at the solar system as an exoplanetary system is whether there are two habitable planets in this solar system, one or, possibly none. And this is now touching on Rob Calder's work. Rob, you'll probably hear somewhere. Hey, Rob. This is recently accepted work looking at the presence of ozone in the atmosphere of Venus. So Venus presents a number of mysteries, and one of which is the mixing ratio, the abundance of ozone in its night side atmosphere. So this measurement here is the abundance of ozone in the night side atmosphere of Venus, which is about kind of ppm level ozone. This blue line is a model of Venus's atmosphere, and tells you what you expect the ozone abundance to be in Venus's atmosphere, which is orders of magnitude lower than what's actually observed. Now, this ozone mixing ratio in Venus's atmosphere is strikingly similar to the ozone abundance in Earth's atmosphere, where we know this ozone is supported by oxygenic photosynthesis and the production of dioxygen by life. So what's going on here? Is this further evidence for life on Venus? Well, what Rob did is look at the chemistry of ozone production on Venus, which links to many species in the lower atmosphere of Venus, critically water, and ultimately the combination of dioxygen with singlet oxygen to produce ozone, and looked at how by varying all of this chemistry, the abundances of various of these species that contribute to the cycles that produce and destroy ozone, and also some of the thermochemistry behind it, is there any scenario in which we can understand the observed mixing ratio of ozone in Venus's atmosphere? And this figure summarizes the results, the ozone mixing ratio up at ppm levels, simultaneously looking at the amount of dioxygen that's produced. And the vast majority of attempts to increase the ozone mixing ratio in Venus's atmosphere fail to meet the ppm levels observed. Only in extreme cases can you get to ppm level ozone, at which point your orders of magnitude, you're exceeding the upper limit on the oxygen, the dioxygen mixing ratio, by orders of magnitude. So what this says is there's an observation of ozone in Venus's atmosphere, and we don't know what the cause of that is. We can't yet, with an abiotic model, a model of the chemistry of Venus's atmosphere that's not got any life in it, it's just got the chemical reactions we expect to be happening, we can't see how to produce the observation. So the kind of caution then from ozone in the context of this diagram is that perhaps our false positive rate given basically an Earth-like planet, for ozone as our biosignature is not this little region, it's actually potentially much larger. Venus is telling us to be cautious in our use of ozone as a biosignature in this case. And in fact, Venus has many mysteries to it. It's long been known in the UV that there's absorption features in the atmosphere of Venus which are not understood. Phosphine, of course, has been detected. It's not understood what the origin of phosphine is, and we've just emphasized the ozone. So the message from Venus is you've got a planet overwhelmingly similar to Earth, yet the chemistry of its atmosphere is very hard to fully understand. And all of these observations, in some sense, have overlaps with the fingerprints of life that life would have on these planetary atmospheres. Yet, given the context, it seems hard for me to interpret any of these as actually being good evidence for life. What they are, to use the language of Carol Cleland, they're anomalies. They're misfits with our abiotic models, but that doesn't make them good evidence for a biotic explanation. It merely means that our non-biological models are failing to match observations. And this kind of is a theme that I'll come back to perhaps a bit later on. But it's context that might reassure us that with these various mysteries of Venus, we're not seeing life, that we're in fact simply seeing chemistry in a planet that we've yet to fully understand. The question, obviously, less so for Venus, more so for exoplanets, is how do we know what the context is? For Venus, it's somewhat simple, although it was really only in the 1960s that we knew that Venus was the hostile planet it is. How are we going to develop this context for exoplanets? And really decide whether our context is this or down here. Like, should the biosignature be very unlikely to be associated with life given the context, or pretty likely to be associated with life given the context? And a really fundamental piece of context in our search for life is the habitable zone. This is a way of viewing the habitable zone, which I'm sure is a concept you've all heard of repeatedly, is as a key piece of context in our interpretation of data, of observations, of biosignatures from exoplanets. This background graphic is the TRAPPIST-1 system, the 7 roughly Earth-sized planets orbiting around the TRAPPIST-1 M dwarf, only a few tens of light years from Earth. And very roughly, this is the habitable zone in this system. 1, 2, potentially 3 planets lie within the TRAPPIST-1 system's habitable zone, and obviously are therefore prime targets in our search for life. What the habitable zone is in our kind of Bayesian framework is our prior. What's the probability of aliens given the context? In a sense, this is kind of how we can use the habitable zone in this same probabilistic framework. If we were to sketch that, what we're kind of saying is that we've got some finite probability of life over in this region within the habitable zone, but outside of it, we think it's very unlikely there's going to be life there. And what this would mean is that, if we looked in detail at any of these planets, I think our lesson from the solar system is we're likely to find anomalies on every single one of them. That's the result of looking too hard at anything, is that things start to look a bit peculiar. I think we discount, we'd likely use the habitable zone concept to discount those anomalies as being potentially biological in origin in these planets, and we'd be likely to start thinking about those anomalies as biological in origin in these planets within the habitable zone. Bearing in mind the fact that we run the risk of a false negative when it's life as we don't know it, that is actually challenging our concept of its requirements in terms of energy, temperature, pressure, or what have you. Now, the habitable zone is just a hypothesis. We don't know for sure where the habitable zone lies, where its boundaries lie for rocky planets. That's something, ideally, we'd like to use exoplanetary observations themselves to constrain for us. But we can use the solar system again as a guide to how we might go about constraining the location of the habitable zone, and therefore this probability of aliens given context, this prior that we're going to bring into our kind of Bayesian analysis of the likelihood of any given signal being good support of the presence of life. And the very similarity of Earth and Venus, both in their physical properties, but in where they lie with respect to the sun, gives us an excellent opportunity to understand where the edge of the habitable zone lies. Here we've got one planet which apparently lies slightly too close to the sun. It's got a 100-bar atmosphere of CO2 and a surface over 400 degrees C. And obviously we've got Earth with just 1 bar nitrogen-dominated atmosphere and temperate surface conditions. And it seems sort of trivial, like looking at Earth and Venus. It seems like it should be easy then to go and look at rocky planets around other stars and see which ones are Earth-like and which ones are Venus-like. But actually, it's not easy. It's surprisingly difficult. And our own history of thinking about Venus, I think, is evidence of how easy it is to be misled. This is an artist's impression of the surface of Venus, I think about 1904, and we're seeing a wonderful kind of tropical landscape with kind of dinosaurs carrying people around like buses, and lots of just generally exciting looking stuff happening. They're having a chat about something down here, and this art was not just, it was not some kind of crazy imaginings. It was, supported by, serious scientific thought about what Venus was like. So there's this text, The Destinies of the Stars by Arrhenius, which says of Venus, we must therefore conclude that everything on Venus is dripping wet. So there was like credible scientific thought in support of Venus being a kind of a swamp, like a kind of swampy world. And this was enabled by the fact it's so cloudy, the fact that those clouds may have been water clouds and globally encompassing cloudy sky, water cloud skies, which kind of supported this dripping wet surface. And it was only, like I said, in the 1960s with microwave observations from Venus that it was realized that the surface could potentially be 600, 700 Kelvin. And then really only with actual missions to Venus that the definitive evidence that those clouds are not water clouds but clouds of sulfuric acid that really ended our picture of Venus as possibly being inhabited by this wonderful kind of menagerie of dinosaurs. So, our own history of thinking about Venus as a habitable planet is a kind of cautionary tale as to how easy it might be to tell Venus from Earth when faced with far less adequate observations of exoplanets, when we have so much less data to go on. This paper from Amori Trio from a year or two ago now kind of illustrates the problem in a different way. There is this 100-bar CO2 atmosphere on Venus, which is, its defining characteristic, which distinguishes its climate from that of the Earth. And CO2 is a very strong absorber. So if we look in wavelength and look at the radius of the planet, then we should see a kind of strong absorption feature, or the planet look a kind of larger radius because of the presence of CO2. And that's what we see in these peaks here. The problem is that CO2 is such a strong absorber that 100 bar of CO2 looks about the same as 1 bar, 1 Earth atmosphere with ppm level CO2. The feature height is very similar in both cases. So using the presence of CO2, the fact that it's thousands of times more abundant on Venus than on Earth in their atmosphere doesn't actually give us the kind of clear sign of looking at a Venus compared to an Earth that you might think it should do. However, I think there are fingerprints on Venus-like planets that can help us distinguish Venus from Earth and so identify where that habitable zone should be and where we should place our prior for aliens given context. And I think what we actually need to look for is signatures of uninhabitability, which is really looking for signatures of Venus-like planets, finding all of those, and then the planets outside of that are potentially the Earth-like planets. And the fingerprint comes not from the CO2, which, like I said, is sort of too is too degenerate with ppm levels of CO2 compared to hundreds of bar of CO2. It's actually from the rich sulfur chemistry of Venus's atmosphere. So, and this is work that has been done extensive in collaboration with Paul Rimmer, and Sean Jordan, Teresa and Sean have worked on this as well, and obviously Rob recently with his ozone work. But what we see in the lower atmosphere of Venus is sulfur species that exist, that simply don't exist in Earth's atmosphere. They're very rapidly removed from the atmosphere. Most importantly, sulfur dioxide and carbonyl sulfide, which exist almost not at all in Earth's atmosphere. Now on Venus, what happens is this sulfur dioxide is broken up by light, producing oxygen and SO. The oxygen reacts with the SO2 to produce SO3, which reacts with the water to give us the sulfuric acid. So it's photochemistry operating on these sulfur species in Venus's atmosphere that give us this opaque cloud layer that masks the surface of Venus from us and led us to believe it could have dinosaurs on it as recently as 100 years ago. Now, this is a problem because it blocks the surface of Venus from our sight. It's also a problem because it actually scrubs, this photochemistry scrubs lots of these species from the upper atmosphere of Venus, the region which we can actually probe by remote observation up here. They've been broken down by photochemistry, so they're barely present in the upper atmosphere. Now, what this looks like, if you perform a calculation or look at the data for Venus, these grey squares, in this case looking at carbonyl sulfide, is that you've got quite high mixing ratios of these spectrally active species near the surface that are then very rapidly depleted by orders of magnitude when you get up into the photochemical region. And that's because of the bright UV illumination of Venus by our fairly hot star. What Sean has shown in his work is that actually this is not true for Venus-like planets around cooler stars, around stars like M dwarfs. These are sufficiently cool, the UV flux is diminished sufficiently that actually these key kind of fingerprinting sulfur species can survive to the upper atmosphere and enable us to potentially distinguish a Venus-like planet from an Earth-like planet, provided it's around a sufficiently cooled star, so these M-type stars, which are the stars that we've got the best prospect for searching for life on rocky planets around. So there's a happy coincidence there. And recently, Sean's kind of built on this work and looked at a compilation of M-dwarf stars and the prospects for searching for these fingerprints of uninhabitability on these stars, and actually many of them are amenable with sufficient observations to actually identify whether they've got Venus-like planets around them, and so identify potentially the inner edge of the habitable zone, and so empirically calibrate our context where we should be looking for Earth-like planets that can support life. But that work is all in this kind of framework of context being deterministic, that we can look at a planetary system, we can look at how far the planet is from its star, and we can know whether it's habitable or not, because that property of being habitable is determined by things we can see today. We can determine how much light a planet receives from its star today. So if that's all that matters, then the probability of aliens given context, is entirely deterministic. However, Teresa's work has really nicely highlighted how context itself can be historic and stochastic. It could be contingent upon things we can't know from looking at the system or looking at a single planet in the system today. And examples of that would be the early pre-main sequence and main sequence lifetime of a star, where its activity could have been very different to today, and that stellar activity has potentially profound implications on the survival of atmospheres on planets. Or it could be something like a stochastic bombardment flux to the young planet that sculpted its atmosphere, delivering nitrogen, removing water, that is really important for whether that planet actually, albeit Earth-like today, superficially, has any prospect of hosting life. In our sort of simple statistical kind of view here, what it means is we've got one planet. We're not sure whether the context is like this, actually very consistent with it hosting life and being habitable, or whether the context is like this, actually more likely to be uninhabitable, with the biosignature then coming from abiotic processes, perhaps those very same processes that we just looked at, like early UV luminosity of the star. So how do we deal with context that's historic and stochastic, we can't see today? Well, fortunately, there is a sort of solution to this potentially built into nature, and that is in not looking at planets in isolation, but looking at planets in the context of the system they occupy. And this is a compilation of multi-planet exoplanetary systems, and what this study is pointing out is when you have multi-planet systems, how frequently those planets are similar to each other or have a systematic structure to the planetary architecture. And this is a really powerful property of the system, because it means if a random thing has affected one planet, some of these random processes will have affected all the planets similarly, such that we can sort of calibrate our understanding of the stochastic abiotic processes by looking at the other planets in the system as well. And we can then ask the question, is our biosignature, our potential biosignature, a result of abiotic processes that have affected every planet in the system? So to look at this in more detail, this is figures from Teresa's recent paper on comparative biosignatures. What we're really doing is trying to use the planets in the system. So this is, say, looking for the potential biosignature as a function of, say, heliocentric or stellar-centric distance. Maybe that biosignature is the presence of oxygen, say, in the atmosphere. Now, there's an abiotic route to filling an atmosphere with oxygen, and that's simply to split water. And the hydrogen escape to space, and that can leave you with a lot of oxygen. And that kind of process would be driven by early UV luminosity of the star. What we might expect to be produced by that is that the planets closest to the star have the highest abundance of oxygen, because they've experienced the most intense UV illumination and have produced the most massive abiotic buildup of O2. Now, these planets, which we know to be outside the habitable zone, provide a kind of abiotic baseline, a baseline against which we can then test the properties of the planet that is in the habitable zone. So if we put the habitable zone planet in, and we see it has an anomaly in its oxygen abundance compared to this abiotic baseline, then we've potentially got an anomaly that could be understood as being biological in origin. If we have a model for what biology can do in terms of accumulating oxygen in a planet's atmosphere, so we've got models that are abiotic, and they fall over where that data point lies, then we might conclude that, well, the amount of oxygen we're seeing in this planet is anomalous given the abiotic processes that the planets in the system have told us have occurred, but it's consistent with what biology can do. However, it's also possible that the observation doesn't match either our abiotic models or our biotic models, and it's just an anomaly that we can't explain with either scenario. And that brings us back to phosphine. That's sort of a bit like phosphine in the context of Venus. It's an anomaly with respect to essentially everything, both the biological and non-biological models. So just to end, I want to kind of comment. So we've looked at context and trying to find, establish how we can determine context in exoplanetary systems using the solar system frequently as a baseline with which to inform ourselves. And Teresa's work really nicely explores how we can use the multiplicity of planetary systems to try and create context empirically from the planets in the system. The final thing I want to talk about is what do we do when the context is alien to us as well? So most of the talk so far I've been touching on rocky planets, planets for which we have important analogues in the solar system with Earth and Venus. Where the current frontier of JWST observations have landed us is not really in probing in detail the chemistry of rocky planets, and certainly not rocky planets around sun-like stars. Where we've landed with JWST observations in terms of the ability to perform deep characterization of atmospheres is in a regime for which there's no analog in the solar system, and that's sub-Neptunes. So planets intermediate in mass between Neptune and Earth. And so here, the context for these planets is alien to us. Everything we want to know about sub-Neptunes, we're going to have to learn from observing them as exoplanets. Obviously, the physics and chemistry of Earth-like planets, the physics and chemistry of Neptune-like planets provides important guides, but we're going to nonetheless be applying it to a regime where we only have, the kind of motes of light coming through the atmospheres of these distant planets to guide our understanding. And this is a real challenge then for interpreting the data we get from these objects as potentially being a sign of life, because we are uncertain in the context of the planet. And what that's led to is, in the case of sub-Neptunes, a variety of hypotheses for what the structure of these planets may be, whether they're Neptune-like, whether they're extensively made of water, or whether they're rocky with potentially very hot climates. And there's obviously a kind of an active discussion on all of these areas, and this is just a sample of the literature, most of which, these articles here that kind of come from the IOA, that touch on the difficulty of establishing context for the sub-Neptune population. And I think in our framework that I've kind of tried to kind of guide this talk around, the situation we're at with sub-Neptunes is, given the debate, the context could be either one of these circles. In this one where, maybe it's got a liquid water surface, we see an anomaly, a signature, which we think there's good reason to believe is associated with life. In the other context, a context where the planet has a molten surface, we'd see that same anomaly, but we'd be trying to understand it in the context of this false positive region, the chemistry and physics of a planet which we presume to be lifeless, and we imperfectly understand. And so the anomaly is telling us something about the imperfections of our abiotic models. So just to sum up now, and hopefully leave some time for questions, I think what I really think is our search for aliens, our search for life, should really be, currently, given the state of the field, rooted in a search for context. I think that's really what we have the opportunity to solve with this generation and next generation's telescopes. What that means is we've got the opportunity to really empirically determine what habitability is and where it emerges in the galaxy. With exploration of the solar system, we have the opportunity to identify how frequently habitability translates to inhabited, with exploration of Mars and maybe with exploration of Venus as well, thinking back to Venus's past. And linking more broadly to prebiotic chemistry, there's this question of the abiogenesis rate. And what we really also need to make sure is that the conversation with the prebiotic chemistry, indeed the biology, that calibrates our understanding of what's required environmentally for life's origin and for life's perseverance is well understood. So how ignorant are we? How big is this region of life as we don't know it? We need to keep testing our understanding of how complex self-sustaining systems can emerge from simple chemistry to have a better idea of where that context kind of bubble lies. So I'll just end with the people that did all the important work, Teresa, Rob, and Sean. This is just a sample of the papers that underpin some of my thinking for this talk, and thank you so much for listening.
Thank you, Uli, for an excellent talk. We have a few minutes for questions. Are there any questions? Yes, Max?
Great talk. Really enjoyed it. Thank you. I was trying to understand better this small overlap between aliens and biosignatures. So, for example, if life on Earth originated in hot vents and deep under the ocean, would you expect, in that case, there to be no biosignatures in the atmosphere?
Yeah, so...
Could you repeat the question?
Yeah, of course, yeah. So, yeah, the question was about the overlap between biosignatures and aliens, and maybe I'll go back to one of the sort of simple slides at the beginning to think about this. And whether we'd expect a biosignature if life originated under the ocean. So, yeah, so I think you're exactly right. What I've been fairly abstract about what biosignature is throughout most of the talk. And I think where that circle lies then is critically dependent on what it is you are looking for. So if life originated under the oceans and continued to live under the oceans, it's perhaps much less likely that biosignatures like maybe ozone would be something that you'd be using here. So the ozone biosignature would perhaps then have very minimal overlap with the alien circle here, for example. But actually, in that context, maybe the biosignature you should be looking for would be carbon monoxide or methane or something. So reduced gases, say, could in that case be or carbon dioxide even, could be the combination of carbon dioxide and methane could be the biosignature. So there's a lot to unpack in terms of what biosignature means, and then how significant its false positive rate would be. Going back to phosphine as well, phosphine was something in an Earth-like context we thought would have a very low false positive rate. So yeah, you can, depending on your choice of biosignature or your mix of biosignatures, you can in principle move that circle around and have greater precision, diminish your false positive rate. Yeah.
Thank you.
Other questions? Yes?
Thanks, really interesting. I've got a question about quantifying sort of the context for the biosignatures, I guess given that we're looking at it in a Bayesian sense. And I'm thinking when you showed sort of the habitable zone and then you had sort of probability of habitable zones to across, for example, the trapped planets. When we do stuff like that, for example, we tend to do at the moment quite a binary sort of like yes, no, here's the line kind of thing.
Yeah.
I propose we go beyond that.
Yeah, I think you're totally right. We're basically using it as a boxcar function, almost for target selection. So the Bayesian framework in that sense is a way sort of articulating in a different way what we're doing, kind of implicitly, I think, because I totally agree with you. I think to go beyond that, we need to kind of define habitability, or we need to bring the actual specific planetary context into habitability, so that there's a kind of systemic habitability, which is that kind of naive green box, within which then you could locally calibrate and inform a spatially dependent habitability if you understood the structure of the planets. So with knowledge about the atmospheric mass fraction and its composition, you could be much more nuanced in where the width of that habitable zone and indeed how likely life is to exist across it. So yeah, we know. I mean, your own work has shown the sensitivity of climates to things like atmospheric mass fractions and the mixing ratio of potential greenhouse gases like H2. If we had that spatially resolved data within the system, we could have a much more nuanced construction of the habitable zone. But I agree at the moment that the concept is largely serving to capture the implicit decisions we make about where to look for life or not. And I suppose that kind of example with the TRAPPIST system was rooted in a rocky planet context, where the habitable zone is the habitable zone for Earth-like planets, where we know what the mechanisms are that stabilize their climate against runaway in either direction. I think, as obviously we touched on with the sub-Neptune work, it's much harder, or it's a different physical chemical system. It's a different habitable zone you're looking for when you change the type of planet. It could lie in a different place.
Yes, okay.
From your interactions with chemists and biologists, what is your sense of how easy they think it is to make life on other planets?
Well, I guess they keep trying, so I guess they must have optimism. I'm not sure I know the answer to that. And I don't know how easy it is to know the answer from a kind of bottom-up experimental approach. I suppose what the bottom-up experimental approach has told us is, despite everything we know about life from deconstruction of extant life, getting back to it from first principles, from building simple building blocks, is evidently enormously challenging. So, yeah, us as the intelligent designer, we're evidently not yet intelligent enough to get ourselves from building blocks to life. I think my hope is that exploration of the solar system provides an empirical answer to that, both through exploration of Mars, but also the icy satellites, which potentially going to have missions going to them. There we have water in a very different context, beneath a thick ice shell that's possibly never been exposed to direct radiation from the sun. It's sort of maybe like the kind of extreme hydrothermal vent scenario, which has been obviously a popular scenario for the origin of life for decades now. We have the opportunity with these two very different worlds, early Mars and the icy moons, to understand whether life can, if just the presence of liquid water is enough for life to emerge. I strongly suspect the answer is no. That's my kind of intuition, certainly for the icy satellites. But yeah, that's not an answer, but that's just my kind of thoughts in response to that question.
I guess I was thinking not necessarily in the lab, just in general, kind of life on the planet.
Yeah. Pass. Yeah.
Okay, one final question. We have 1 minute left. Yes?
Yeah, thank you for your talk. It's really interesting. In this part of the talk, you talk about there are lots of more diversity of kind of life. So, for example, if maybe life can form by not carbon-based but silicon-based, and then maybe you can live in not water-based ocean but methane ocean or things like that. So, how far do you think people understanding of this diversity of life goes?
Yeah. So this kind of speaks to the life as we don't know it, and how much space should be given up to our ignorance, basically, of life. And again, it's sort of for me, it's an unknown really.
Yeah, so are there already lots of publications about this kind of stuff, or not really?
Yeah, I mean, so the synthetic chemistry has indeed been producing or working on life as we don't know it, with different types of informational molecules to the ones that we use. And obviously there have been discussions around replacing phosphorus in life, trying to replace carbon in life, none of which has been sort of enormously successful in actually demonstrating that life would ever emerge with this fundamentally different kind of atomic fabric to our own life. And part of that is probably is facing the same problem we were just discussing, which was even sort of reproducing life, the origin of life event in the lab with known biochemistry is proving extremely challenging. So to do it with a sort of alien biochemistry where we don't even know what we're aiming for, is basically, as far as I'm aware, not really being significantly attempted. Which is not to say there isn't life as we don't know it. It's just that it's hard to quantify. I think more likely the region occupied here, in my mind, would be like technological life. It will maybe life that is the product of originally carbon, oxygen, phosphorus-based life, but it's then the computers that took over and then are doing their own thing with imprinting different signatures on the surface and atmosphere of the planet than the biological life that gave rise to them. But yeah, that's sort of speculation.
Okay, just one last piece of information. There's a lunch outside, but this is for the IOA Wednesday seminars. So if you join that will take place here in about half an hour, 45 minutes. Okay, so let's thank Oli again. Thank you very much.